Yeah, thanks all for coming, and I'm very happy that I am able to open this workshop with my presentation. Just a remark, I'm a little bit sick, so I hope my coughing isn't disturbing during my talk. Yeah, so I'll be talking about a formalization project that is not finished. Actually, it has barely started. And sort of my key takeaway of this talk is, if you're interested in joining the formalization, I would be very happy if you do. The result that I want to formalize is called Carleson's theorem. This is a result in Fourier analysis, and because Fourier analysis is probably not not everyone is very well acquainted with that, I will keep this talk pretty high level and mainly talk about the high level concepts, and I don't want to go into nitty-gritty details. But this week I will also be leading a working group which I should still add to the Google Doc, but if you want to join, I can explain more there. So, to start out, let's start basic with the definition of the Fourier transform. I can imagine that some of you haven't seen this since a while. So I'll be talking about functions. I don't know why it's doing this.
Are you connected via a wire?
Hmm?
Are you connected via a wire or via some...
Wire.
I am wired.
Okay.
Yes. I had some problems in the beginning.
Okay.
Well, let's hope for the best.
Yeah.
Otherwise, I'd scream for help.
Yeah. So I'll be talking in my presentations only about functions from R to R. This can be generalized. You take a function, and let's say that the function is integrable. Then you can define the Fourier transform so that returns a new function, and it's this integral transform. So you take the function at x, multiply it by this funny-looking exponential, and take the integral over all x, and then this function. This is a new function now in psi. And so, the sort of idea you should have with this is that, you decompose functions into different frequencies. Like for every psi, you have a different frequency, and then the value of the Fourier transform tells you how much of that frequency exists in the in this function. So this gives you the Fourier transform. And so there's also the inverse Fourier transform, which is very similar. It's actually almost the same, except instead of a minus sign, I just don't have a minus sign here. And other than that, it's exactly the same transform. So this Fourier transform has some very nice properties. Here are a few. Under some conditions, if you take the Fourier transform of a derivative of a function, this is up to a constant. It's basically multiplying the Fourier transform by psi. So the Fourier transform of the derivative is psi times the Fourier transform of the original function times some constants. And if the functions if you have two integrable functions, you can take the convolution, which is another sort of expression involving an integral with both f and g. And then the Fourier transform takes the convolution to just the product of the two Fourier transforms. And then another result that I sort of want to focus on more this talk is the Fourier inversion theorem. So this is actually already a mathlib. This was added by Sebastian Guezel a couple months ago. it states that if you have a function that's integrable, it's continuous at a point x, and if you assume that the Fourier transform of f is also integrable, then actually the inverse Fourier transform is actually an inverse of the Fourier transform. So then taking the Fourier transform of f and then the inverse Fourier transform of that gives you the same function back, or at least at x, and so if f is continuous everywhere, then this gives you everywhere the same function back. And sort of these properties make Fourier transforms very useful to solve when working with differential equations, because if you want to, so one possible technique in principle to solve a differential equation is to apply the Fourier transform on both sides. Then all your derivatives just become the same as multiplying it by a variable. Then you can sort of try to solve that equation of the Fourier transform like algebraically, and then you can apply the inverse Fourier transform to get your original function back. But to what extent that, I mean, this doesn't, of course, always work in practice if you want to compute the actual differential equations, but this is sort of why one application of the Fourier transform to get, to solve differential equations. So now, what Carleson's theorem is sort of asking is, does this result hold more generally? This Fourier inversion theorem, because there are sort of three conditions: that the function is integrable, continuous, at least at a point, and the Fourier transform is integrable. And actually this last condition is kind of strong, because here's an example. Let's take a very simple function. I just take a box, so I take the interval from -half to 1/2, and just take the characteristic function of that. So that's a box function. And this has Fourier transform the sine of xi over xi. And this is a function that is sort of oscillating, but actually it's not integrable. And so the Fourier inversion theorem doesn't actually say anything about this case, whether sort of the inverse Fourier transform of this function gives you back the original function. But sort of in this example sort of shows that very simple functions already have like Fourier transforms that might not be integrable. So the Fourier transform, we want to sort of get a result with weaker assumption.
Can you take the Fourier transform of that? Can you inverse Fourier transform sin x over x?
Well, that's a good question.
Okay, sorry.
Because so the definition I showed before.
Yeah, I just didn't understand the punchline of this example.
Yeah, so the definition I showed before, this sort of takes the integral over the whole real line, and this sort of only makes sense if this is integrable, which follows if f is integrable, but otherwise it probably is not true. But indeed. We want to define that is actually exactly the
okay.
You can define the Fourier transform for a wider class of functions by not taking the integral over the whole real line, but just taking the integral from -r to r.
And if the integral exists, then it will be that limit, but the integral might not exist, and the limit might still exist anyway.
Exactly. Yes. So you can define sort of the Fourier transform only on the bounded interval for a wider class of functions. Then you can take the integral from -r to r. And this, for example, this always applies when f is always makes sense if f is continuous, because then it's integrable on the variable. And then you can consider the limit as of gr as r goes to infinity. And I will answer questions after I finish this slide, because I might be answering your question next. Because what does this limit exactly mean is very important. So we can choose sort of how, what limit we consider. We can take a pointwise limit of these gr, so we can just take the limits of this expression as r goes to infinity as a function of xi. but sometimes, like, that only gives you certain examples. So another case you want to consider is, say, L2 functions. So here is the LP norm of a function. So the LP norm of a function is just take the absolute value of the function, raise it to the power of p, and take the integral over the whole real line, and then take that integral to the power 1 over p. And so another important case is L2 functions, so that functions that are square integrable. And then we don't want to consider this limit of GR pointwise, but we want to consider it with respect to this L2 norm. And for other P's, this is also relevant, but L2 is sort of the most basic one, other than integration. But so it matters like how you consider this limit, so whether it's pointwise or L2. Do you still have a question?
Yes. So that's supposed to fix the problem when the function is not integrable at plus or minus infinity, right?
If it's not integrable over the whole real line, yes.
Yeah, but when it's not integrable, for example, at 0, this won't work. So
Yeah, so this is still.
That's considered.
If you're not like locally integrable, then this still doesn't work. You can do other kinds of Fourier transforms, like of distributions. I won't go into to that in this talk, but indeed, so there are generalizations also for these cases. But this works for all continuous functions and for LP functions. Okay, and so this is also already sort of almost what I said, or part of this slide is already what I said last slide. So if f is an L2 function, so that means that the L2 norm is finite, then I can define the Fourier transform indeed using this limit as a limit of these functions on the last slide with respect to the L2 norm. And that is a well-defined new function, like L2 function. So at least L2 functions are sort of defined almost everywhere. So two functions are identified in L2 if they're almost everywhere equal. And so at least the Fourier transform is then defined again as an equivalence class of these things, of these functions. And so if the function is in L2, then the Fourier transform in this sense is again an L2 function. And indeed, we have a version of the Fourier inversion theorem, namely that if I take the inverse Fourier transform, which is again like this limit, so I can define it in the same way on the last slide, generalize it to L2 functions. And if I do take the inverse Fourier transform again with respect to the L2 norm, then sort of that limit converges in the L2 norm and converges back to F. At least, so, yeah. But that doesn't guarantee that this limit sort of converges pointwise, because pointwise convergence is stronger than L2 convergence. And so this sort of result is so this is roughly Plancherel's theorem, or at least part of this. And that is a pretty basic result, but it doesn't tell us about like the pointwise convergence.
When you say pointwise convergence, it means it's almost everywhere.
Yes. So that will So when talking about indeed pointwise convergence here, I mean almost everywhere pointwise convergence. And so
Is it important that the bounds are symmetrical when you take the limit?
It is not. In fact, like if you have any sequence of integrable functions that tends to your L2 function, the Fourier transform will have the same limit. So limit of that
Take
sequence.
minus R to R, so
You could really go from minus R to 2R.
That would also
Okay.
give the same results.
It's like elementary, but it is really an extension by continuity of.
Yes, so yeah, exactly. Okay, so Carleson's theorem is precisely this result, but with pointwise convergence almost everywhere. So if you have a function that is in L2, then this Fourier transform, so I can take the Fourier transform of f, which again lives in L2, and then I can now take the inverse Fourier transform, but with the limit taken pointwise, and then that limit converges to the original function value for almost every x. So I'm not very happy that I sort of wrote here basically the same as what I wrote here, but it's a very different statement. So in both cases, I'm taking the limits of these functions gr, but so Carleson's theorem is about these limits, but almost everywhere pointwise, and the sort of the more basic result is just with L2 convergence, and these are sort of miles apart in difficulty. So this result you will see in like any basic textbook about Fourier analysis, somewhat rigorous. And this result you will see in almost no textbook, just because it's like an incredibly hard proof, and sort of notoriously hard in Fourier analysis. And then there's a slight generalization by Richard Hunt 2 years later, which is that you don't have to require that f is in L2, you can require actually that f is in LP for p strictly greater than 1 and less than or equal to 2. And then you get the same conclusion. So you can take the Fourier transform again with respect to the LP norm, and then sort of the inverse Fourier transform. Pointwise converges almost everywhere to the original function.
So is it now what happens for p bigger than 2?
Yeah, then the Fourier transform might not exist as a function, but only as a distribution. Even just writing down the Fourier transform of f is already problematic in that case.
Floris, maybe this is very mundane, but you could say this theorem is literally Abel prize work.
Yes.
Carleson got the Abel prize for this theorem.
Okay,
For his whole career, but
Yeah.
he's big.
Yeah.
And almost everywhere is in the sense of measure theory as used in Lebesgue.
Yes. So the set of points where sort of the limit in this inverse Fourier transform doesn't converge to the original function value, that is measure 0. So here are some remarks, and that is basically, yes, this is as difficult, and sort of all the conditions are required. So, for example, that almost everywhere is important. Like there are L2 functions that are even continuous L2 function where the limit diverges for some values of x, and in fact, for all measurable, like for all null sets, you can find a function that diverges exactly, or at least on a superset of those points. There are notice that in the sort of generalization for LP, I require that p is strictly greater than 1, and that is because it fails for p is equal to 1. So if you only require that the function is integrable, then this expression might, like the limit in the inverse Fourier transform might diverge for every x. So it doesn't fail a little bit, it just fails completely for certain functions. Even if you consider sort of if you're more familiar with Fourier series, like you consider a periodic function, then you can define Fourier series with Fourier coefficients, which is not a function but then a sequence. Then you can consider the same problem, and that is equally hard and sort of analogous. And so, for example, if you have a continuous periodic function, then and take the Fourier series of that, then you can consider the partial Fourier sums, and that limit might also diverge everywhere. If you add like continuously differentiable here, then your function is sort of nice enough, then everything will be fine. But so the sort of the difficulty here is that like what happens with all the functions that are like continuous but not smoother than that. Also another result that you might have seen is that if you don't take the limit of the Fourier series but sort of the average of the first n elements of the Fourier series, so this is talking again about the Fourier series, and you take sort of the average of the first n terms and then take the limit as n goes to infinity, that does always, or at least that converges to the right value, at least if the function is continuous. And this is, again, a pretty basic result.
So Floris, that you're doing Cesar summation for the transform and the inverse. And why do they come out the same?
So for the Fourier coefficients, you don't have to. You can just define them normally, okay. And then for indeed you do the Cesaro summation for the inverse. Okay. And also, I only restricted in this talk to functions in one variable, and that is because actually in more than one variable things also get tricky. So because you have sort of more flexibility over like what, you integrate over some shape and then you want to blow up the shape to infinity. And actually whether the result holds in that case depends on the shape. So if you just take boxes as a shape, then you can sort of generalize Carleson's theorem to that case if you then let the box go to infinity. But if the shape is spherical, then it's actually an open problem whether that holds. So, I'm not telling you why the proof is hard, but I'm sort of giving you like very sensible statements that are very close to the theorem, and they all fail. So that should have give you an idea that there's some subtleties going on here.
Is there do people believe that spheres are okay? Or?
I don't know. Actually I don't know. Yeah. So this is a result I want to formalize. Partly because it's very hard, and partly because I have been in discussion with Christoph Thiele, another professor here in Bonn, and he proved sort of a generalization of Carleson's theorem like last year with his like group. And so then sort of this problem tackles both like a current research problem and like a classical hard result at the same time. So I want to formalize this generalization and then derive the standard result from...
Oh, so you're going to formalize the generalization?
Yes.
Okay, great.
Yes, so so the preprint of this paper appeared on Archive like a bit more than a month ago, but we have already had discussions since then, talking about formalizing. And actually, so originally they had a preprint that they hadn't published yet. That had like a 30-page proof of the generalization. And then we sort of started formalizing it, and we realized, because I'm not an expert in Fourier analysis, that there are like quite a lot of hidden steps that are sort of routine. And then Christoph's group sort of started like rewriting the whole proof with like much more detail, so that it should sort of be understandable for non-experts, like a blueprint that we've seen for other projects.
Are you getting them to write the blueprint?
They have written the blueprint, right. Yes. So they've written a very nice blueprint. Now the proof is 100 pages. And plus 30 pages proving classical Carleson's theorem from the generalized version. So it's, yeah, so the project has gotten quite a bit bigger, yeah, so...
I have a question.
of this work is it's already online. Yeah,
Did
question.
you start getting interested in Fourier transforms a month ago because the preprint was out? Or
No, I already started this.
discussion before?
I already started discussions like last October with him, because Christoph Thiele is also very interested in formalization as an outsider. He sort of shares our goal that like at some point all papers should be formalized before they get sent to, or I mean some of our goals that papers should be formalized before they should be sent to journals, or at least they can be formalized if you want to sort of fast track them maybe to journals.
That's great.
Because then checking formalization, like checking a formalized proof is of course quite a bit easier. And then like reviewers can focus on sort of is the proof, like is the result important and relevant. So here is a very standard template and blueprint following the framework by Patrick Mousseau. So you can click on the blueprint. This gives an HTML version of this, the 130-page blueprint that's about Carleson's theorem. So it's split into 10 chapters. And actually, the sort of proof structure is kind of nice. So chapter 1 sort of just states the problem and gives all the definitions for this generalized result. Then chapter 2 states sort of 6 propositions that are needed in the theorem. Then chapter 3 proves the result from these propositions, and then all the next 6 sections or next 6 chapters are all proving one proposition individually. And so sort of everything from section 3 to 9 are sort of independent of each other. And then chapter 10, which turned out to be quite a bit longer than expected, is a proof of the classical Carleson's theorem from the general version. We also have a dependency graph that is again automatically generated by Patrick Stoel. You can see it's quite big. And there's already some green nodes because I have a student, actually a bachelor student, that is doing his bachelor thesis trying to do the reduction of the general Carleson's theorem to the classical statement of it. And so the green nodes means these are already formalized. And we haven't updated all the sort of circles that are green. So a green circle indicates that the statement has been formalized, but the proof has not been. And there should be a few more green circles. And then
When green means no proof?
so green means it's proven. But then a green circle with a white.
Oh, I see, the green border. Gotcha.
And yeah, you can see the dependency graph is quite big. But actually, what's also interesting is that sort of the sections are sort of visible. So there's sort of 6. So there's sort of a diagonal here that is the 6 propositions in section 2, and then there's individual trees you can almost see here that are like proving that proposition. And there is only a little bit of interaction between the proposition, between the different proofs of the different propositions. And then here, this metric space Carlson is the statement. I'll jump to the LaTeX version. Is the statement of the general Carleson's theorem, the generalization they provided. And actually, this statement is more general, but it's also a lot more complicated. So I'm not going to explain what this statement is in detail. Yeah, so it holds in sort of a setting where X is a doubling metric measure space. So this is a metric space together with a measure, which is a doubling measure. So the sort of the measure of a ball with radius 2r is bounded by some constants of the measure of balls of radius r. And then there's a whole lot of other data and properties you need. And then the final conclusion is that there's this Carleson's operator, which is again some integral transform, but then also taking a supremum over some boundary conditions. And the main result is proving that this Carleson's operator is a bounded operator. So it's not a linear operator, but it is bounded. And even in Carleson's original proof, this idea of like having an operator that you prove to be bounded is sort of the main idea of proving Carleson's theorem. And so under a whole lot of conditions, the conclusion is indeed that this so this is the L1 norm of the Carleson's operator applied to F. This is bounded by some complicated constant times some measures of sets we're interested in. So, I mean, this statement, I don't want to go through all details, but this is the result we want to formalize and derive the classical versions of Carleson's theorem from. And so I am not a Fourier analyst. If you're also not a Fourier analyst, or if you are, but you know some formalization and you're willing to join, feel free to join. There's a lot of bubbles and there's a lot of parallel work that can be done. So you're welcome to help. I think I already mentioned all of this about the blueprints. Then I want to mention some sort of observations of this project. That this project is a little bit peculiar. That's sort of this is a collaboration of Fourier analysts that barely know any lean and formalizers that, I mean, symmetry-wise, I want to say barely know any analysis, but at least are not experts in analysis. And it's sort of an open question how much friction this will cause in the formalization. And so two things I've already noticed is that the blueprint is definitely not written with formalization in mind. Like if you're an expert formalizer, you sort of already try to write things a bit differently, thinking about, oh, this is the way, the direction I want to formalize. And so that requires like reformulating maybe some statements a little bit to make them a little bit nicer to formalize. And that can be tricky, especially if you're not an expert in the area. You don't actually know if you reformulate, is that result still true? But yes, I will definitely...
Kind of important.
That is important. But yeah, I will definitely be in contact a lot with Christoph, like asking things like, oh, if I change this thing a little bit, is it still true? But actually one thing that is interesting is that when formalizing, you care about these things, and sometimes you ask these questions that mathematicians are sort of not interested in or unaware of, like, oh, can you sort of drop this condition or weaken this condition, and then like it's not the kind of question that like a mathematician typically thinks about. And so these conversations we've had are sometimes not can be a bit interesting because this is sort of not the way that like mathematicians typically think about this. And so I want to my aim is to show that like some current research and analysis is like feasible to formalize now. Of course, we cannot do everything, but like this is a sort of well chosen topic that like is feasible to formalize. One thing I should mention is that sort of the blueprint is now this 100-page document, but it is self-contained and should contain like all the proofs beyond Mavlib in that blueprint. So it's not like referring to like another like 100-page paper that is an ingredient in the proof.
So the mathematical part of the team are very interested in it because they have doubts, or because just as a benevolent gift to the formalizing community.
I don't know. So they don't really have doubts about like the proof up to like small errors, but they like there's no serious doubt that like the proof is wrong. And this is mostly the goal is to sort of demonstrate like that like current research in Fourier analysis can be formalized. Thanks.
And the author don't have doubts, but maybe other people have doubts. Do they try to convince other people with that?
Is the paper published?
So no, this is not published. This was the sort of the blueprint appeared on Archive like a month ago, and so it has not been submitted for publication yet.
Oh, so the paper is not even. Is there a preprint? A regular preprint?
There is a preprint on Archive. Well, so there was a regular preprint, but actually the version posted on Archive is the sort of the blueprint actually.
The PDF generated by the blueprint, as it were.
Yeah. I mean, there was a LaTeX PDF before, and that turned into the blueprint, but yes.
So the 30-page version is replaced by the 100-page
Yes.
version. So
the
they-
30-page version is not online anywhere, I believe. Let me finish my talk.
Okay, I'm sorry.
Good. Yeah, so the one remark I want to say is that one thing that will be tricky, and that I also need to think about a bit, is the Mavlib compatibility of the project. Because so the blueprint, like in Mavlib, we sort of want to generalize all definitions to appropriate generality, and the proof is very much written like proof this particular theorem. And so my plan is actually to formalize mostly like their theorems and their results, mostly as they are stated, and then sort of try to, after the fact, generalize them to Mavlib quality and incorporate at least parts of the proofs into like Lean's Mavlib. We could do it the other way around, like first try to generalize on paper and then put it in Mavlib, but actually I think that is not less work, and this has the advantage that if you have a working proof and generalize it, then you can sort of, hopefully with roughly the same proof the general version, or see where it goes wrong. And therefore, for non-experts, it's easier to generalize once you already have a formal proof. At least, that is my hypothesis. One thing that will be tricky is probably parts of the proof will not become part of Mavlib because it will be a lot of work to generalize everything to the appropriate generality. But hopefully, like there's definitely a bunch of like ingredients that are sort of standard results in analysis that I definitely aim to incorporate in Mavlib once they are formalized. Yeah, and so in conclusion, this is formalization of current research and at the same time a hard classical theorem, and feel free to join. And I'll make a Zulip stream on Zulip sort of coordinating the work. Thank you.